A quick review of probability. A reminder about the language. So we have a scenario, a 6-sided die is rolled. Find the probability that the result is an odd number. So the trial is a single experiment. So in this case, the trial is a 6-sided die is rolled. The sample space is the list of outcomes from the experiment. The outcomes, of course, are the possible results of an experiment. Sorry about my dodgy writing, I'll fix that. The sample space is the list of all possible outcomes for an experiment. It can be designated with S or X or all sorts of different letters actually. It gets curly brackets, and of course the sample space is 1, 2, 3, 4, 5, 6. It is the list of all the possible outcomes. The event is the probability, the situation that we're looking for the probability of. So the result is odd is the event. Now a favourable outcome is an outcome that matches that event. So the favourable outcomes for this are 1, 3 and 5. And I might get asked for the set of favourable outcomes when of course you'd list it like that. A complementary event is the opposite of an event happening. So in this case, since the event was the result is odd, the complementary event is the result is even. So it's the opposite of the event or the event not happening. So that's just a bit of a reminder on some language that we use. So theoretical probability, of course, the probability of an event happening is found by the number of favourable outcomes over the total number of outcomes. Now we can use some slightly more mathematical notation for that, but we don't need it for this first one. So obviously, for example, in this scenario, there are 3 odd numbers, so there's 3 favourable outcomes. There are 6 total number of outcomes. It's 3 out of 6 is the probability of the event being odd. It's worth noting that, for example, if I've asked for the probability of getting a 1, which is obviously 1 out of 6, the probability of not 1, which can be done with this little apostrophe notation, yes, you could just count up all the not 1s, that's 1, 2, 3, 4, 5, or you could do 1 minus the probability of actually getting 1. 1 minus 1/6 is 5/6. So often it's useful to use those complementary events. The probability of an event's complement is 1 minus the probability of the event. We also have experimental probability. This is calculated in the same way as theoretical probability, but it uses the result of an experiment. So it's when we have, for example, counted the number of cars passing in different colours or something like that, because we're unable to get any meaningful theoretical probability. And it assumes that the set that we looked at for the experiment, in the experimental probability, gives us a representative answer. So for this one, of course, the probability of an event occurring is the number of favourable outcomes that occurred and because we did trials, we divide by the total number of trials. So you'll remember, of course, a trial was one single run of an experiment, so we can do the experiment over again. We can roll a die 15 times, whatever that happens to be. So, for example, if I've tossed 3 coins and counted the number of heads and tallied that in a frequency table, I could get 0 heads, so I could get tails, tails, tails with my 3 coins. I could get 1, 2, or 3. I'm just copying this example from the book, sorry, I should have written it in before. So this is the number of results we got. So 0 heads turned up 11 times. There was 1 head and therefore 2 tails 40 times. So basing a probability on this would be experimental probability. So the probability of 0 heads is going to be that happened 11 times out of a total of 100 trials. Adding those up gets me 100. The probability of, say, fewer than 2 heads would be 1 head or 0 heads, so less than 2 heads. So either 1 head or 0 heads would satisfy that, so that would be 51 out of 100. About the only other tricky one that you might get is the probability of at least 1 head, and that would be anything that didn't have 0 heads, so you'd add up all these options here.